Today's learning objective is about the phase rule two component systems. The phase rule is to study the behavior of the heterogeneous systems, and it was proposed by William Gibbs in 1874. Phase rule helps in studying heterogeneous equilibrium systems with two or more phases that are in repeat. In the two component system, before explaining, let me give you the definitions for a phase, components, degrees of freedom. Phase, it is denoted by P. It is denoted by P. Its phase is another part of a system which is homogeneous, physically distinct by a boundary surface and mechanically separable from other homogeneous parts of the system. Example, mixture of two or more gases or mixture of two or more miscible liquids are homogeneous. So phase is one. Water plus petrol. See, I'm giving you the example before starting these components. Before starting these components, I'm giving you examples. I'm giving you the examples of what is phase, component. So phase, example, you take water plus petrol, water plus petrol, water plus benzene, CCl4 plus water. So the phases are two. The phases are two. And calcium carbonate, if you heat, you get CaO and CO2. CaCO3 gives rise to CaO and CO2. P is 3. The phases are 3. Sulfur, rhombic, monoclinic sulfur. The phases are 2. I is water, water vapor, phases are 3. Ammonium chloride, ammonia and HCl. The phases are 2. Next, we'll see what is a component. It is denoted by C. Number of components in a system, it is the smallest number of independently variable constants by means of which the composition of every possible phase in a system can be expressed with chemical formula. Number of components in a system is small number of independently variable constituents by means of which composition of every possible phase in the system can be expressed with a chemical formula. Water has three phases: ice, water, water. C is 1, P is 3. Sulfur system will take. Sulfur system has four phases: monoclinic, rhombic, plastic, vapor. But all the four phases have same composition, that is S, sulfur. C is equal to 1, P is equal to 4. We'll take one more example for components. Calcium carbonate system. Calcium oxide plus carbon dioxide. Here in this system, each phase is expressed with any of the two constituents. Calcium carbonate has a composition of CaO plus CO2. Calcium oxide, CaO plus CO2. Carbon dioxide, no CO, CaO plus 1 CO. So the C is 2. C is 2. Now ammonium chloride will take solid. It gives rise to ammonium gas plus HCl gas. Again, in a closed system, ammonia and HCl are in equal amounts. Composition of 2 can be expressed as a single component. C is equal to 1. Open system, C is equal to 2. Sodium sulfate system, you take The CS2, sodium sulfate and water. But phases are many. So these are examples for two components. Now, for the two component system, when the two independent components are present in heterogeneous system, the system is referred to as two component system. According to phase rule, two component system has one phase. F is equal to C minus P plus 2. This is equal to 2 minus 1 plus 2 is equal to 3. Two component system having one phase will have 3 degrees of freedom, or 3 variables would be required to define the system. So the 3 variables are pressure, temperature and concentration. It requires 3-dimensional phase diagram for study of two component system. Now let us simplify the study two component system. It is in the condensate system. A condensate system can be studied by reducing comparatively less, more important variable. This reduces degrees of freedom system by 1, and system can easily be studied with the help of two-dimensional phase diagram. Now we'll take example of two component system. Solid lead, solid silver, and solution of molten silver and lead and vapors. Lead and vapors. Now the boiling of the silver and lead are high. Vapor pressure of the system is very low. The vapor phase can be ignored and the phase can be studied as a condensed phase. This system can easily be studied with the help of two-dimensional T bond C diagram and the reduced phase rule equation. Here, this is the reduced rule equation. F prime is equal to C minus P plus 1. C minus P plus 1. The system, it is generally studied at constant pressure. The phase diagram of the lead silver system is shown in the diagram.
In the class.
Here we are having the variance of the temperature on the y axis, and on the x axis we are having lead and silver system. This is the temperature and here it is lead and silver system. Here you are having G, D, H, C here. Again A, C, B. Here F. Now A, C and B, C, B. You are having AC is a solid level. This is the this complete AC. You are having solid lead plus melt of the lead and silver, and BCF we are having solid silver and melt of lead plus silver. Now ACB we are having melt of PBN AG solution. PBN AG solution. Here C is the eutectic point, and the bottom one, this complete one, you're having solid lead and eutectic mixture, and this portion is solid silver and eutectic mixture and eutectic mixture. In this two component system, the reduced phase rule is being applied, which is condensed system, reduced phase equilibrium for this condensed system. The gaseous systems involve large change of volumes. These are affected by pressure. But the systems having only solid and liquid phases are not considerably affected by the pressure. So solid liquid systems with the gas absent is called condensed system. The degree of freedom in this system is reduced by 1 because vapor pressure of solid is very small. The experimental measures, if you take for the temperature and the compositions are carried out at atmospheric pressure, the reduced equation has become F prime is equal to C minus P plus 1. F prime is degrees of freedom, variables for two components, that is solid liquid temperature compositions. So solid liquid equilibrium I have preferred here. Two components completely miscible. The portions are two components completely miscible, two components partially miscible, two components immiscible. Based on the nature of the solid phases that get separated out during cooling the system, this type can be divided into following types. Two components do not form any compound, and on solidification they simply form intimate mixture known as eutectic mixture. Two components do not form any compound, but on solidification they simply form intimate mixture known as eutectic. The example of this one, lead, silver I have taken. Still there are examples: potassium iodide, water, lead, antimony, bismuth, cadmium system, zinc, cadmium systems. The two components combine to form compound with congruent melting point. That is, two components form solid component called intermetallic compounds. Yeah, that one I gave you the example, magnesium and tungsten. And if incongruent is formed, and that is sodium chloride and water system. Now, this diagram will represent for you. This diagram, complete one, represents the phase equilibria of two component system, lead, silver system. The two component system being lead and Ag, various possible phases are solid silver, solid lead, solution of Ag and lead, vapor. In Ag lead system, boiling points of both Ag and Pb are high. Vapor pressure is practically absent. So the effect of pressure is negligible. Effect of pressure is almost negligible. The system, it is a condensed system and reduced. It is a condensed system and it is the reduced phase rule. The condensed phase rule. So F is equal to C minus P plus 1. This is the rule that is being applied for the whole diagram. Now let us have a look onto the curves, the point, and the areas in the phase diagram. The phase diagram of the lead silver system consists of the following curves. As explained, AC curve, it is a freezing point curve of lead. AC curve shows variation of melting point of lead on addition of silver. You are adding silver and the lead is getting freezed out. AC, the freezing point curve of lead. Again, in this AC curve, the melting point of the lead on addition of the silver. So pure lead melts at 327 degrees centigrade. That is point A. So addition of silver, you keep on adding silver. Adding silver, it lowers the melting point. Addition of the silver, it lowers the melting point along the curve AC. The added silver dissolves in molten lead to form. The added silver dissolves in molten lead, forms AgPb solution with the separation of some part of the lead, solid lead. Here, as you are adding pure lead, it melts. So addition of silver lowers melting point. Addition of the silver dissolves molten lead to form Ag silver solution and separates the lead. So addition of silver will give you solid lead. Therefore, two phases, solid lead and AgPb solutions remain together in equilibrium along the curve AC. So the phases are two here, solid lead phase and melted AgPb solution. These two are in equilibrium, solid lead and melted PbAg solution. Both of them are in equilibrium, remains together along AC curve. So the phases 2 solid lead and molten Ag solution. The components are 2 Pb and Ag. So C is equal to 2, P is equal to 2. Now we'll apply the reduced phase rule. F prime is equal to C minus P plus 1. F prime is equal to C is 2, P is 2. 2 minus 2 plus 1. The system is univariate. Now we'll see for the areas. Later on, we'll have a complete look onto the curves. Okay, we'll see the curve AC. As I've told you the curve AC. Similarly, we'll see curve BC. BC is the freezing curve of Ag. Freezing curve of Ag. You are adding lead. So Ag and there is a melt of lead and silver. There is a solid Ag and melt of Ag and Pb. Here, this is the curve. A here, the curve is BC. The curve is BC. The second curve, BC. We are adding, this curve shows variation of melting point of Ag on addition of Pb. This is the melting curve of Ag on addition of Pb. So you're adding lead, thereby silver is getting precipitated. Solid silver gets precipitated. And for this BC curve, it is in equilibrium with solid Ag and melt of Pb and Ag. Now we'll see. P is equal to 2 phases for this AC BC curve. Phases are 2. One is the melt, the other one is solid AG. C is 2, PB and AG. So therefore, when you apply the formula, again the same. C is equal to 2, P is equal to 2, F prime is equal to C minus P plus 1. This is equal to 2 minus 2 plus 1. This is equal to 1. The system is univariate. So for both AC curve and for both BC curve, you get the same variant systems. That is univariant systems. Now we'll see for curve curve AC and curve BC we have seen. Now what is the eutectic point? Here I'm showing you the eutectic point P. Then you're having PB, AG, melt. Eutectic curve. Here, this is eutectic point. There you're having AG, PB and the complete melt. AG, PB and complete melt you're having. And for this eutectic point, this eutectic point is lowest temperature. Eutectic point, this is the lowest temperature at which liquid mixture of two components exist in equilibrium with their solid phases. AG solid is in equilibrium with solution. Solution is in equilibrium with lead solid. As I've told you, you're having AG solid, PB solid and solution. So at the point P is equal to 3, C is equal to 2, F is equal to C minus P plus 1. F is equal to 2 minus 3 plus 1 at a eutectic point. F is equal to 0. At this point, the system is invariant, non-variant. It is invariant and non-variant. At eutectic point, in AG lead system, T is equal to 303 degrees, C is equal to 2.4% AG plus 97.6% PB. So you will be getting at this point the system is invariant. Now we'll see eutectic mixture. A liquid mixture of two components which has lowest freezing point compared to all liquid mixtures of same components. So the liquid mixture that exists at its eutectic point is called eutectic mixture. So the composition of the components at their eutectic point is called eutectic mixture. And for lead silver system, eutectic composition is 2.6% Ag, 97.4% lead. Now let us have a look onto the areas. Area BCF. This area consists of two phases, BCF. BCF. In this area, you are having solid AG and the melt. Solid AG and the melt. Hence, it is univariant system. C is 2. The phase is 1, 2. Here, this one. C is 2. Phases you are having solid plus melt. Again, that is 2. So, C is 2, P is 2. 2 minus 2 plus 1. univariate system. Now we'll have look onto the area DCFH. This area DCF. The area DCFH. DCFH. This complete area we'll see. I've told you this area, now this area. In DCHF, area has two phases: solid silver crystals, solid eutectic crystals. CS2, PS2. Solid silver crystals and solid eutectic crystals. Even the eutectic crystal is solid. Yeah. CS2, PS2. Phases are 2 and composition is also 2. The system becomes F is equal to C minus P plus 1. CS2, PS2, 2 minus 2 plus 1. Univariate system. Univariate system. Now let us see area CEDG. CEDG. The area has solid silver. CEDG. CEDG. This area. First this is the area, second this area, now this area. CDGE. You're having solid lead plus eutectic crystals. Two phases, two components. The system is F is equal to C minus P plus 1. 2 minus 2 plus 1 is equal to 1. It is invariant system. Sorry, it is univariate system. It is univariate system. Now, what are the areas that are remain? ACE and BCF. ACE, ACE, and BCF. Already BCF area is discussed. BCF is discussed. Now ACE will see. You're having solid lead, melt of Ag plus Pb. So CS2, just like BCF, even for ACE, CS2, PS2. So F is equal to 2 minus 2 plus 1. 1. This is univariate system. Univariate. For eutectic point, it is invariant. For the curves, it is univariate. Okay, almost everywhere it is univariant except of the eutectic point, that is eutectic point you're having only invariant system. Now, area above ACB and area ECF. Area above ACB, this one, above area above ACB. Above area ACB, complete liquid melt we are able to see. Only liquid melt is there. So CS2, P is 1. CS2, P is 1. So F is equal to C is 2. 2 minus P is 1. Only liquid is there. So 2 minus 1 plus 1. 2 minus 1 plus 1. Yeah. So area above ACB, it is the liquid melt. Number of phases are 1. So it is 1. And the components are 2. Here you can see A, C, B. Only liquid melt is there. Here only the liquid melt. 2 minus 1, it is 1. 1 plus 1, it is 2. Bivariant system. I am repeating, area above ACB, it is complete liquid. It is complete liquid. P is 1. Only one phase, P is 1. So F is equal to, see, two components I told you, 2 and phase is 1. 2 minus 1 plus 1. 2 minus 1 is 1. 1 plus 1 is 2. Therefore, area above ACB, you are getting liquid melt, that is bivariant system. Bivariant system. Now, area ECF will see. ECF, above this complete one, ECF. We'll see for that. You are having lead, silver, both of them in solids. So, the phases are 2. You are having the melt plus solid. And the components are 2. 2 minus 2 plus 1. Univariant system. That's it. I hope you have understood completely about the areas. Only here it is bivariant. All these areas you are having univariant. And even on the curves you are having univariant. So having two component system, as I've told you, two components, if there is no reaction takes place, if there is no reaction, there is no any reactants of two components, they are completely miscible, but there is no reaction. Such type 2 components do not form any component solidification, they don't react. They simply form intimate mixture called eutectic mixture, that is lead silver system. In this system, we have seen, we have applied the phase rule, reduced phase rule, and on the curves you are getting univariant. On the areas ACE, GCD, CF, HD, and BCF, it is univariant systems. For the curves as well as for these 4 areas, it is univariant system. And for only one area, you are getting, that is above ACB area, you are getting bivariant system. Okay, for the curves and for the 4 areas, univariant. And for this one also univariant. But for the curve above ACB is, you are getting bivariant system. And at point C, we are getting eutectic mixture, eutectic point. Here, all are invariant except the above area liquid bivariant. And eutectic mixture is invariant system. Now let us see the desilverization of the argentinoferrous lead. It is Pattinson's method. Now, using this one, this process we have used, recovered the silver from argentinoferrous lead. The ore you are getting argentinoferrous lead. From that, we have recovered silver. In that way, we have applied this phase rule. This method is called Pattinson's process. From the ore argentinoferrous, we have applied our phase rule. We have recovered silver. This is called Pattinson's process. This involves desilverization of lead in accordance to the diagram, phase diagram. So argentinoferrous contains small percentage of silver, very less, 0.1. From this, we have heated above the melting point, liquid melt consisting of the lead silver solution is obtained. Now, silver lead solution is cooled. Then PB continues to separate out and regularly it is removed. At the end, the eutectic solution it contains 2.6%. See, every now and then the silver lead solution it is getting cooled. So lead, due to its melting point, it's getting separated out. And regularly as the lead is getting separated out, we are removing the lead from the solution, ore solution. Argentinoferrous solution, we are separating the lead continuously. So as we are separating continuously, so what it is, as you're separating continuously, regularly the lead is removed, and in the end, the eutectic solution contains 2.6% of the lead, and this is obtained. So the above process increases the percentage of the silver in the argentinoferrous lead. So therefore, the eutectic mixture containing 2.6% of the silver, it is treated by recovering silver profitably. This way we are using, in this way we are using our phase diagram. We are applying our phase diagram, this principle, and by Pattinson's process, we are desilvering. We are recovering silver from argentinoferrous lead. Okay, argentinoferrous lead. So this is the two component system, and from the two component system, I have explained you the lead system, and the lead diagram is being, yeah, the two component system. It is being explained, two component system, lead silver system. We have applied it for desilverization process. I hope everybody have understood today's class. Thank you all for sparing your time for listening my lecture.